Okay, so let's recap what we have said yesterday. So yesterday we started to introduce the coordinate system. And the coordinate system represents indeed the main basis that you need to know when you want to deal with the attitude of a spacecraft. So the main reference frame that we have introduced was the optical bench coordinate frame, so the OBF. OBF in this course is treated as the main reference frame of the spacecraft because our main purpose is to reorient the payload, the scientific payload with a specific accuracy. So the transformation between OBF and the spacecraft body frame is basically assumed known. So what I mean is that in terms of rotation matrix, you have that, so let me write on this one. So that the rotation matrix between the OBF and the spacecraft body frame, so let's write BF, is known. So I use this kind of nomenclature. So basically, this R is the rotation matrix. The lower on your left, bottom left, you have the one of the two reference frame. So the reference frame that you want transform to. So basically, if you multiply a vector that is, let's say, a vector A, this is defined in the OBF, what you have is that this vector is transformed to the rotation matrix to the body frame. So this is the kind of formalism that I use. So basically, the rotation matrix from the OBF to the body frame is known. What I mean is that the body, so the optical bench frame, for example, in this spacecraft, is so basically is focused in here, and we have said that the x-axis of the optical bench frame is indeed aligned to the bore side. So the only transformation that you need to pass from the OBF to the body frame of the spacecraft is indeed well known, because it is assumed that the optical bench is rigidly supported by the spacecraft. Here probably it is not really straightforward, because you can see that the optical bench frame is really large. So you can have indeed some offset in reality. The other thing that could not be fully true is that sometimes you have that the optical bench frame is movable. So basically you don't have a rigid platform, but you have something that moves in order to be reoriented and to permit the spacecraft to to look at the specific region of the observed body. So anyway, the main thing here is that what we need to do is to determine the attitude matrix, what we are going to call A. So the A matrix is indeed the rotation matrix, in our case, between the OBF to the inertial reference frame, EF. So this is basically what is our major goal. And we can do that because we assumed, for example, that the rotation matrix from the OBF, so the optical bench frame, to the body frame is well known. So now look, let's use the example of the ISAT spacecraft, in which we have a laser altimeter. So why we need to know these attitude metrics with a very high accuracy? Because basically the task, the scientific task of that instrument really depends on the accurate knowledge of the orientation of the platform. Let's assume, let's recap of how the laser altimeter works. So the laser altimeter is given by a laser transmitter that sends a signal to the planet, and by receiving the signal from the planet through the telescope, is able to determine the light of time, and so the distance, relative distance between the spacecraft and the body surface. By measuring that, you're able to reconstruct the topography of the planet. However, the topography is not really only the thickness of a specific relief that you have. So let me answer the question afterwards. So the laser altimeter basically has this telescope that has to point to the surface, and the main problem is indeed that you're not only estimating the vertical direction, but you're also affected by the slopes of the topography. So usually when you measure a topography, you don't have a flat terrain. So for example, this one, but you have a certain inclination of the terrain. So if you have an error in the attitude, what happens is that, for example, let's say 1 arc second. So 1 arc second is, so 1 arc minute is 1/60th of a degree. 1 arc second is 1/60th of an arc minute. So it is 1/3600 degrees. So it is a very small amount of angle, and you need to know this tiny angle in order to don't introduce errors of a few meters on your measurement. So for example, let's assume that you have a slope of 1 degree here. From your attitude, you should be 90 pointing. So basically, you should be able to look at the surface vertically. But if you have an error in the attitude matrix, you have, for example, an error of 1 arc second. You have that your instrument or your spacecraft is pointing with 1 arc second of error. So basically is measuring this distance instead of that one. To assume, to determine which is amount of the error induced by this attitude mismodeling, we have to determine which is the altitude of the spacecraft. So I thought it was about 600 kilometers. So if you have an error of 1 arc second, and you multiply it by 600 kilometers, you have an error horizontally. So this error here of about 3 meters. So this is about 3 meters. So if you have a slope of 1 degree, you have that basically vertically you are doing an error. So basically what you're doing is this vertical error here that can be approximated by these 3 meters times the tangent of that angle. So the discrepancy of the vertical distance between this one and this one is about 5 centimeters. But if you have a slope of 3 degrees, you have an error of about 15 centimeters. You have to take into account that usually the laser altimeter measurement can approach accuracy of about 10 or 30 centimeters. So what it means here is that if you have an error in the attitude of few arc seconds, you are introducing an error in the vertical distance that is larger than the error of the instrument. So the attitude plays a major role in the accuracy of the instrument, and in particular in the accuracy of the laser altimeter, but it could be the same for a camera. So the attitude represents indeed one of the major tasks for spacecraft operations. So let's look at, so I received a question for the coordinate transformation. So it would be also necessary a transformation between the origins of each system. Well, in the attitude problem, the knowledge of the center of the spacecraft. For example, the knowledge between the two reference frames. So, for example, if the reference frame is this one and the other reference frame is this one, is not, I mean, it is important if you want to determine, for example, if you want to combine the attitude and the orbit determination problem. Let's do an example. So when you want to determine, for example, the orbit of the spacecraft, you also need to know the attitude, because of the attitude, for example, it will change the perturbative effect. So let's assume satellites around the Earth. If you have an error in the attitude, so you have to know the attitude of the solar panels in order to determine the drag effect. And usually what you need to know is to report everything to the center of mass in order to not induce, so in order to integrate the center of mass position of the spacecraft. But in terms of attitude, what really matters is the orientation of the reference frame. So what we want to do indeed is to reconstruct the orientation rather than the position. The knowledge of the center of mass and the orientation of the spacecraft is also another subject. It's called robotics, because when you want to do a transformation matrix in robotics, you have a combination of rotation and translation. If you are going to do the robotic course with me next semester, you will have indeed that you don't only introduce the rotation matrix, but what you have already seen in other courses, you introduce a transformation matrix. The transformation matrix is a combination, so it's a 4x4 matrix. It is the rotation matrix, so this is a 3x3. And here you have the offset, let's call it P. So it's a vector that is the offset between the two center of the reference frame. And this you have here 0, 0, 0, 1. Anyway, this is out of the scope of this course. What we want to do here, we are only focused on the orientation of the matrix of the spacecraft.
Excuse me, can I ask a question about the result of this the attitude requirement? I mean, if I understood correctly, you said that by making attitude error, we can commit a measurable error that is even larger than the spatial instrument error. Did you mean that? I didn't get
Exactly. So we have to
that was
think.
done for small angles. No, but we can go further and then be larger than 3 meters. So did you mean that?
Yes. So what? Yes. Basically, the concept is this one, but the idea is that when you want to design an instrument, for example, that could be a scientific or even an instrument for telecommunication or other services, you need to provide some requirements. And requirements, one of the main stringent requirements are related to the attitude. So what I meant, as you said, is that when you design an instrument, so if you have an instrument that has accuracy of about, for example, 10 or 20 centimeters, you have to be sure that your attitude is not going to give you errors that are larger than the accuracy of the instrument itself. So in this case, we know that the laser altimeter has an accuracy, for example, of let's say 20 centimeters. Usually on Earth, you have also slopes of about 5, 6, even 10 degrees. On those regions, if you have errors, so if you have a requirement on the attitude matrix, so that you need to know the knowledge of the attitude with an accuracy of 1 arcsecond, it means that your instrument is going to see errors given by the attitude because the accuracy of the measure of the instrument is lower than the errors introduced by the attitude. So, briefly, when you want to design a spacecraft, you have to be careful that the attitude, the requirements that you need from the attitude control system fulfill the requirements of the instrumentation or the spacecraft operation. So what we are going to see next is that we have to design sensors and actuators that enables the accuracy that are well suited to fulfill the mission constraint. So for example, let's do an example in this case. What we will need to do is that since we know that we have slopes, so inclination of the terrain larger than 3 degrees, we need to have sensors and actuators that provide accuracies lower than 1 arcsecond. That is fundamental. So basically, the main point here is that we need to design the attitude control system take into account the requirement of the instrumentation. And that's an important point. So I hope this explains what I meant before. So here we are trying to design the attitude control and the sensors of this system in order to fulfill specific requirements. So when you do this kind of work, you don't have only to take into account the requirement of the instrumentation. The other constraints are related to, for example, cost, mass, and volume of the spacecraft. So you need to do a compromise between the much more accurate as instrument, so much more accurate sensor, and the compact version of the sensor. That's the reason why we're going to look at all those sensors and see for each specific task what is the best option. So we have to take into account that we will need a specific orientation knowledge, but on the other hand, we also need to not provide, because for example, an easy answer for all the mission is that, okay, let's put star triggers on the spacecraft. They will provide a milliarc second knowledge of the attitude, and so we are able to determine the attitude correctly. Well, it's not always possible, and all missions have different possibility, have different allocation of the mass instrument, different cost. So we have to take into account all of those constraints. Okay, so if that answers your question, we can go ahead and start the attitude kinematics. So here I will give you a brief introduction to what we're going to see. Because of course you already have done all these in other courses, so I don't want to repeat many things that you already treated in other courses, but I will focus on specific topics that will be used in, for example, the attitude determination, but also in the attitude control. Okay, so let's start with the representation of the attitude. So what we have said is that our goal is to determine the attitude matrix. So the attitude matrix is assumed to be the rotation matrix between the body frame, or the OBF, to the inertial frame. There are different representations of these attitude metrics, but the main representation is the cosine, director cosine. So the direction cosine is indeed provides the basic introduction to the problem. So let's see. Okay, still recording. So what we are going to see is that the attitude matrix can be represented in different ways. So the main representation is the direction cosine. And so we know that the attitude matrix is given by 6 different elements. So 96 different elements, but we know also that those elements are not independent. The cosine direction cosine enables a fair representation of the attitude matrix that is also helpful when we want to introduce other methods, for example, the Euler angles or the quaternions. The main representation that we are going to use are the quaternions. So in order to introduce the attitude matrix in terms of cosine, direction cosine, we consider, for example, the inertial reference frame 1, 2, 3, 1, 2, 3, that actually is the inertial reference frame. On the other hand, you have also the reference frame that is associated to the body. So we can call it U, V, and W. So let's assume, for example, that this one is the OBF reference frame. So if you want to represent the attitude matrix, you already know that this matrix is given by U1, U2, U3. So basically, each versor of that body reference frame is expressed to the 3 different axes in the inertial reference frame. So let's call it EF. And this is the body frame that, as I said, could be considered the OBF, okay? And you have, so this one will be V1, V2, and V3. So the reason why I'm writing this down is because that will also be useful when you want to determine the attitude matrix in terms of quaternions. So you have that this matrix indeed enables the mapping from the inertial reference frame to the body frame. So if you take this matrix and you take a specific, for example, let's say this vector A in the inertial reference frame, so if you do A, then multiply A in the inertial reference frame, this gives you the vector in the body frame in the BF, okay? So this kind of representation enables the representation of the matrix in 9 different elements. But we know that these 9 elements are given by 3 versors. So you know that only 6 of them are independent. But in principle, you know that the rotation matrix and an attitude matrix can be represented by only 3 elements. So the A represents the attitude matrix. But we have to find a convenient representation. So this is the attitude matrix. You have to find a convenient method in order to determine the representation of the rotation between the OBF and the inertial reference frame. So the main properties of the attitude matrix are well known. The main property, since it is formed by a triad of orthogonal vectors, is that the matrix itself is a proper real orthogonal 3x3 matrix. Another important property is that, and this is fundamental when you do the attitude, is that A times A transpose is equal to an identity matrix. So that means that the inverse is equal to the transpose. And this is a fundamental properties that you have to keep in mind, although I know that you already know, but I think it's better to refresh these kind of properties because that will be useful afterwards. So you know that this is times A. Okay, so the other main properties of the attitude matrix that is given by the definition with the direction cosine is that the determinant of the attitude matrix is equal to 1. That is another important property and will be important when we're going to introduce the method for the attitude determination. So you have to take into account and account for this property here. I'm not going to reintroduce, but another representation. So this is the direction cosine, this direction cosine, but you can also introduce the same matrix or represent the same matrix with 3 different different rotations, sorry. So the 3 different rotation will be through the Euler angles. So the principle here is that you are able to introduce only 3 parameters in order to determine the orientation of a spacecraft. So another representation here will be with the Euler angles. So the Euler angles are not really I mean, we're not going to use this representation because of the limits that you already have seen during other courses. So the main limitation of Euler angles is that you have basically singularities. So if you want to represent a specific orientation of the spacecraft and you want to do 3 separate rotation in, for example, 1, 2, 3 or 3, 2, 1, you have possible singularities that affect your attitude determination, because for that representation you're not able to have a solution. So we are not going to look at that in particular. There are ways to avoid singularities with Euler angles. So for example, the other approach could be indeed to use a different rotation. So one possible series of rotation, as I said, is 1, 2, 3 or 3, 2, 1. These 6 type of rotations, if you commute all the index, represent a rotation for each of the main principal axes. However, you can also try to find, for example, or rotation through 2, 1, 2 or 1, 2, 1. So this kind of rotation that repeat one of the index. That enables sometimes the possibility to avoid the singularities. But of course, it always depends on the geometry. And so you have, I mean, in the, if you approach singularities, when you integrate, for example, the dynamical equation or the kinematic equation of the attitude, that will be really dramatic. And so you want to avoid that. That's the reason why the main parameters that we are going to look at is the quaternions. The only thing that, so the only times that we are going to see the Euler angles is when we're going to talk in the second part of the course of the control theory. When we are going to look at the passive control of the spacecraft, we are going to use, for example, Euler angles. One advantages parameterization of the Euler angle is indeed by using the roll, pitch, and yaw. So, for example, let's assume that you have, so this is the Earth, and this is the spacecraft, so this spacecraft orbit. So you have your spacecraft that is here, and it's pointing. So let's say that it has an antenna that is pointing towards Earth. And you can, in principle, since you want to keep a nadir pointing of the spacecraft, what you can do is to define the body frame to have that the body frame is very close to the orbital reference frame. So for example, you assume that in the x direction, you have the roll axis, so it is very close to the along track direction. So in this direction, you will have so in x, you will have the angle phi. So this is the other axis, the nadir pointing, and it is called zeta. And zeta give you the yaw angle. So this is roll. So, and this is psi. Psi is the yaw angle. And you have y, that is the pitch angle. So it is out of plane here. And it's called the theta. Remember that, because we're not going to see in the next few days, but they will be indeed seen during the passive stabilization of a spacecraft. attitude stabilization of the spacecraft. The reason why in this case it will be advantageous is because when you want to keep nadir pointing, you want to keep these angles really small. So as you know, the rotation matrix expressed in terms of Euler angles is in terms of the, for example, if you have a matrix A31, that will be an attitude matrix that is function of psi sorry to be so slow, but I prefer to write down in order to have all that. With a blackboard would be really easier. And you have A1 that is the matrix of the roll angle. As you know, these matrices are indeed the rotation matrices. I wrote A, but in principle are rotation matrices. So for example, if we want to write down this one, we know that this one is given by cosine of, so C is for cosine, cosine of the psi, cosine of the psi, sine of psi, and minus sine of psi. And similar expression for the others, although are rotations along different axes. Why I'm writing that? Because if you are able to express in Euler angle, you know that these angles these elements will be 1, so you have a diagonal matrix equal to 1, and the off-diagonal elements are equal to the angle. That simplifies a lot our computation of the passive stabilization of attitude spacecraft, and that's the reason why that could be useful at the end of the course. For now, what we need to do is indeed represent the kinematic equation of the spacecraft. So the best approach that we are going to do in 10 minutes, because now we have a break, is indeed using quaternions. So quaternions represent the main representation that is used to determine the kinematic equation of the spacecraft. Euler angles could be useful when you have to consider a nadir pointing spacecraft, and so you need to have that the body frame is very close to the orbital reference frame. So you need to keep that reference frame very close to the orbital frame, keeping these angles really small. That will be useful later. For now, we need to introduce quaternions, that because it represents the main representation for the kinematic equation. So let's have a break here, and we can have questions now.
Will you please explain again when we use quaternion and when we use Euler?